let's go ahead and take a look at weak acids and their properties and behaviors in solution. So the most pertinent fact about weak acids is that when they are in solution, they're only going to be partially ionized. So this is obviously in direct contrast with the strong acids that we've previously discussed. Basically, when you put a weak acid into solution, only some of it ionizes into its proton and conjugate base. The Ka, or the K value, the equilibrium constant associated with your weak acid is going to indicate the degree to which the weak acid ionizes. And basically, when you have a small degree of ionization, you have a small degree of product, so you subsequently typically have smaller Ks. Okay. Something else to note is that many weak acids have their acidic proton attached to an element like oxygen. And we saw this example when we looked at acetic acid a little while ago, or at least in the last lecture. This is your acidic proton. Okay. Notice it's attached to the more electronegative oxygen, and basically this is an example of that weak acid situation. Now, we do have a list of weak acids that we're going to look at this next slide. You should become familiar with a good portion of them. So the neat thing about the weak acids list is that we don't actually really need to memorize these because basically if your acid is not one of the strong ones that you're supposed to know, it's most likely going to be a weak acid. So the most commonly seen weak acids, at least in most problems that I've ever seen, are hydrofluoric and acetic acid. These are very commonly used in weak acid problems. They're readily available in most chemistry labs and subsequently are utilized in that vein. Okay, I also want you to take a look over here at the equilibrium constants associated with these acids. Notice that they're pretty small. So a very small equilibrium constant is going to indicate that you don't have very many products. Not having very many products is directly related to the low quantity of ionization into H+ and conjugate base of these weak acids. Okay, so Ka, K sub A, is the acid dissociation constant. So basically, it's very similar to the equilibrium constants we've been discussing before. The only difference is that we're specifically looking at the dissociation of an acid in this situation. Okay, so right here we have a generic acid dissociation setup. We've taken the acid, we've dissolved it into H2O, okay, and we've subsequently produced our conjugate acids and our conjugate bases. When writing an acid dissociation constant expression, or the equilibrium expression, obviously we take our products and put them over our reactants with respect to, obviously, whatever coefficients are present. So in this case, my conjugate acid and conjugate base are my products. Okay, and those are going to be divided by the concentration of my acid. Okay, notice they all have coefficients of 1, so the exponents associated with each of these are all 1. Okay, also remember that pure liquids and solids are going to be excluded from K, so in this case, notice H2O has not been included because it's a pure liquid. Okay, now your Ka, right, as we've seen, indicates the tendency of your acid to break apart into its corresponding ions. Okay, now the bigger your Ka value, the stronger your acid. So basically, the more products you produce. The smaller your Ka, the weaker your acid. Okay, so and for most weak acids, you're going to have a Ka value somewhere between 10 to the negative 2 and 10 to the negative 10 typically. Okay. All right, so being able to write dissociation reactions are going to be pertinent for us to be able to write our Ka equilibrium expressions. So if we take hydrochloric acid, obviously this is one of the ones we should know, HCl. Okay, that's going to dissociate into H+. Okay, and of course Cl-. Okay. Now, we could include the water as an individual product, or we could just write our HCl as follows. Okay, if we look at acetic acid, okay, so remember acetic acid. Okay, it's going to dissociate into acetate. Okay, ammonium ion. Okay, it's going to dissociate into ammonia and that proton. Okay, so this species here, okay, we're going to end up with okay, and last but not least, okay, I'm just going to write this one as follows. Okay, so basically these are all of our dissociation reactions for the various acids that we have present here. Okay, and being able to write those are obviously important for being able to write the correct equilibrium expressions. Okay, so something I want you guys to notice is some of the ways that some texts actually indicate the presence of a strong electrolyte or a weak electrolyte. The strong electrolytes, we know that they dissociate when put into water, basically 100%. So if I take sodium chloride and drop it into water, it's going to break up into sodium ion and chloride ion. Okay, and they're going to be dissolved, and that's just the way it is. They dissociate 100%. Weak electrolytes, on the other hand, are only going to dissociate to some degree. So, you know, in this case, we have acetic acid. It breaks up into acetate and our H+ ion. Okay, but the reality of it is that I still have a whole bunch of acetic acid in that container and only a little bit of my products. Okay, so strong electrolyte versus weak electrolyte, that can also be directly connected to strong acids versus weak acids, right? So that dissociation process that we see with electrolytes, same concept is applied to acids and bases. So strong acids, okay, that you should obviously continue to be working on becoming familiar with are the following. In these situations, these strong acids, they behave as strong electrolytes, so they break apart into their ions basically completely. So they ionize, quote unquote, basically 100%. So a lot of times you'll see an arrow that's not double-sided. Okay, it just shows the arrow going to the right because dissociation is basically what's favored drastically. So that's just one of the little things you may see in textbooks. So let's go ahead and let's look at weak acid. Okay, so weak acids, remember we've talked about the behavior of weak electrolytes and how they don't completely ionize. Same thing for weak acids, they don't completely ionize. So you'll have some of your products in solution, but you'll still have a whole bunch of your acid present, okay? And so in this situation, we usually use a double-sided arrow to indicate the presence of that weak acid, okay? All right, and I guess we should probably talk about our bases, okay? Strong bases, obviously they behave similarly to strong acids. They're going to dissociate completely into their corresponding ions. Okay, so they're going to behave like the strong electrolyte or strong acid, okay, in terms of their ionization processes. Okay, so let's go ahead and let's look at how to calculate pH from Ka when we're dealing with weak acids. Okay, so in order to do a weak acid problem, we need to do several steps. So the first thing is we want to identify the major species that are in solution that can actually affect your pH. The next thing we're going to do is use an ice table to figure out the equilibrium concentrations. The next thing is obviously write our equilibrium expression with respect to Ka. Obviously, if we can use the approximation method, we should do so. If not, we need to utilize our quadratic, our calculators, to help us solve for x. Okay, and after we've done that and we've calculated the concentrations of all the species, we can then utilize our concentration values at equilibrium to calculate our pH. Okay, so if we go ahead and look at this problem here, they ask us what is the pH of a 0.5 molar HF solution at 25 degrees C. Okay, so guys, notice HF, that is a weak acid. Okay, and so in that vein, once we know we have a weak acid, we know that we're going to be utilizing our ice table and all that good stuff. So another thing that needs to be provided is the Ka value. Okay, and this will usually be given to you, or you could look it up on a table, you know, in one of the appendices in the back of the book. Okay, so HF, what we want to do is we first want to look at, you know, the species that are going to be involved in this process. So we know HF is going to ionize into H plus and F minus. Okay, taking that data, we can then write our equilibrium expression. Okay, obviously our products over our reactants. Okay, and we know that that's equal to 7.1 times 10 to the negative 4. So we do need to take into consideration the fact that an ice table is going to be needed in order to get from our initial concentrations to our concentrations at equilibrium. Because as we know, weak acids do not completely ionize, so there's only going to be so much H plus in solution dictating our pH. Okay, so obviously we set up our ice table like we've done in the past. Okay, we set up our initial concentrations. We indicate how these are going to change with respect to the ionization process, and we establish the equilibrium values based on the difference in the change and the initial concentrations. Okay, so in that situation, we then take our equilibrium values and plug them into our equilibrium expression. Okay, so we have our x squared because we have H plus and F minus. Both of them are equal to x at equilibrium, so we have x squared there, and then 0.5 minus x was our equilibrium value for HF. Okay, that's all going to be equal to our equilibrium constant. Now, obviously we can utilize, or at least try to utilize, the approximation method. Okay, we're going to go ahead and do it that way for now, and then we'll discuss once again as a quick review of how to make sure that that's okay to actually do. So basically we're using the approximation method because the Ka here is pretty small. So in that situation we're going to drop our x value from our reactant HF. Okay, and we're going to subsequently have our Ka being approximately equal to this expression here. Okay, we then bring this 0.5 up and multiply it by 7.1 times 10 to the negative 4, and that's going to give us this x squared equal to 3.55 times 10 to the negative 4th. Okay, we take the square root of both sides, and that's going to give us our concentration of x. Okay, so we know that x is equal to the concentration of H plus and F minus at equilibrium. Okay, so we subsequently take our H plus and we plug it into our pH equation because that's actually what they're wanting us to calculate. And if we take the negative log of our 0.019 value, okay, that's going to give us 1.72 for our pH of our solution. Okay, so now we need to obviously make sure that the approximation method that we chose is appropriate. So we're going to go ahead and do that on this next slide. Okay, so remember we can try to use the approximation method when our Ka values or K values are really small. Okay, now it is appropriate to use that value when x is less than 5% of the value from which it would have been subtracted. Okay, so we know that from the previous example we had what, 0.50 minus x. Okay, so if the value for x that we solve for is 5%, is less than 5% of 0.50, then we know that the approximation was okay. So what we do is we take that x value, we divide it by our 0.5 molar, multiplied by 100. In that case, that gives us 3.8%. That's less than 5%, so the approximation in that situation would have been okay. Now, if we would have been dealing with a different concentration of solution, same thought process would have been done, and if we would have tried to do the approximation method, right, we would have established that x is equal to 0.006. Okay, 0.006 divided by 0.05 times 100 gives you 12%. So in this situation, the approximation method would have not been appropriate, and you would have needed to use the quadratic equation in order to solve for your x value. Okay, and we've already done these, but just as a quick rehash of how to check yourself and all that good stuff. So in these problems, we want to make sure that we are, first of all, accounting for the fact that if we're dealing with a weak acid, we need to take additional steps. Okay, it's not like a strong acid that ionizes completely. We must consider the fact that the acid is only going to ionize to some percentage. Once we've established that we have a weak acid, we're then going to set up our equilibrium expression and basically our ionization expression with respect to the actual acid and what conjugate acid and base it's going to produce in solution. Okay. After we do that, we set up an ice table. Once we set up that ice table, we then plug in our concentrations that we know. Okay, subsequently solve for our change and our equilibrium concentrations. Once we have our equilibrium concentrations, we plug that into our equilibrium expression. The equilibrium expression will then allow us to solve for x by one of two methods. Either we're going to do the approximation method or we're going to have to do the quadratic method. So if your x value is less than 5% of the value from which it's being subtracted, then your approximation approach is fine. If it's larger, it's 5% or more, then you're going to have to use the quadratic method.